Okay, let's go with addition polymerization. There's two ways that we look at making polymers. Now, firstly, let's think about what a polymer is. What do you think poly means? Many. Mer. I don't know. So many mers is our polymers. But what we are able to do is make a very long chain. So we're talking carbon chain, obviously, for our organic chemistry. And the two methods that we consider, first one is addition. And for addition polymerization, we need an alkene. And if we look at how we're going to set this up so that you do it the correct way every single time, I will show you. Now, just say we start out with the very basic, oh no, we maybe won't do this one. Oh, yes we will. Our first example in your booklets back on page 12 is ethene. Okay, so ethene, should be able to write this one. It's only going to be 2 carbons, isn't it? Now, the way I suggest that you do this is to have the double bond horizontal and everything else vertical. So for ethene, that means I've got, and I'm going to put my hydrogens on in this case. Okay, so all I'm doing is putting the double bond horizontal, everything else vertical. It just keeps it clear so that when you add them together, you can see what's happening. Often questions will ask for 3 repeats. So this ethene that we are reacting is the monomer. Okay, that's our starting compound. So the monomer, mono meaning what? 1. We go from the monomer of 1 to the polymer of many when we join them together. And we need to have a suitable environment for this to happen, catalysts, etc. But what happens is that we break that double bond. This double bond will break and form a new bond in there. And we'll put in that to indicate that it's an ongoing chain. So if I look at my my 3 repeats that I did there, actually I can put that in as a blue bond. So that's what happens, is that we break the double bond and we form a new bond to make a new chain. Some questions will also ask you to indicate what the repeating chain is, or what the repeating part is. And the way you do that is by just putting a square bracket around the repeating part and the letter N in the bottom corner to indicate that you've got N number of that repeating chain. And you don't need to worry about naming, but this was ethene, now we have polyethene, or sometimes called polythene. And so its name is obviously derived from the monomer. If we look at another example, which is question 13 in your booklets, polyvinyl chloride. Okay, so polyvinyl chloride, also known as PVC, is formed when one chloroethene. So if I've got one chloroethene, it's going to look like this, isn't it? Again, I'm putting my double bond horizontally and everything else vertically, so that when I look to see what am I going to make when I polymerize this monomer, it's very easy to see what's happening. Remember that we're going to break the double bond and form a new bond. It's an ongoing chain. That's what's happening now. You don't, in a question, you don't have to show what's necessarily happening like I'm doing. I'm just trying to illustrate it to you so that you can get an idea of what's going on. 2, 4, 6. And I guess if we probably should say that we're using a catalyst for this reaction to occur. But that's not really the focus of the chemistry. The focus is that you understand that this is an addition reaction because we don't have any other product, and we're going from unsaturated to saturated, like we've seen in other addition reactions of alkenes. And if you look at question 13, it does say that it wants you to show how the polymer forms throwing 3 units in your answer. So this is 3 units, because we've got 3 repeats. So addition polymerization is pretty straightforward, really. Has anybody got any questions about that? Or comments? Because the other kind of polymerization that we need to look at is perhaps a little bit more complicated. And this is when we form polyesters. So polyesters are on page 51. So I'll get you to turn to page 51. Now the thing I guess I should highlight or stress is that that double bond for addition polymerization has to be between the carbons. Sometimes I've seen students try to polymerize across a carbonyl group, C double bond O. That's not going to work. Okay, it has to be across the carbons. Right, so with the polyester, we have a different set of requirements. So for our addition polymerization, we needed to have an alkene, and for our condensation polymerization, we need to have a diol and a dicarboxylic acid in general. That's the most common structure of a question for you. You could also have a molecule that had an alcohol and carboxylic acid functional group on the one molecule. Okay, but we want, what we're doing is we are going to be reacting a dicarboxylic acid with a diol, and why do you think its name might be condensation polymerization? What do you think another product might be?
Water.
Yeah, so we're going to form water as well. And so we need to have, again, we're going to have catalyst. This is the generalized form. We're going to have the alcohol like that, remembering that the R is representing a carbon chain, carbon and hydrogen, and we're just focused on the functional group. And now we've got a dicarboxylic acid, same thing, where I'm representing the middle part of the molecule with R prime. And what happens here is this is where we're going to lose the water. And this is happening along the whole length. So that end will go as well, and that end will go as well. Now for the condensation polymerization, you aren't going to be asked to produce 3 repeats because it'll end up huge. But you will be asked to do some repeats. Now if I look at how I'm going to draw this repeating section that I've just produced, I'm going to have a dashed line there to represent the bond that I've broken here. Then my oxygen. Then this section that was my alcohol. But now here we're joining on to this carbon as well. So we can have it as like that. So what does the structure look like? If we replace, let's just have this fairly simple. Do that. If I put the water up here, got a bit more room. Let's just say that's my diol. I'm just going to move this carbonyl group up so that it's a little bit clearer what's happening. And I'm going to make this chain a little bit longer so that we can differentiate it from that chain there. Okay, so hopefully they look more like that clearly as a diol, and this is clearly a dicarboxylic acid. And so now what we're going to do is we're going to dehydrate it. Remove remove that water there, and if I draw the molecule that I am making, I should show you that I'm also, remember, this is going as well, and this is going as well. You can't leave your hydrogens on the ends. So it's going to be O, that as a repeating unit.
Do these have a name, or would we expected to name them?
Polyester.
Okay.
Okay, so this is polymerization of a diol and an alcohol and a carboxylic acid make an ester, don't they? We react them together, and so this is then a polyester, but you're not expected to name it. But you can see these ones are, like the other one with the double bond was pretty straightforward. This one is a little bit more complicated. It's the same mechanism though as forming an ester. It's just remembering that you have to remember that the reaction's happening at both ends. And this is the repeating chain for a polyester. Plus water. So we saw that one was lost out of the middle, but we also lose one on the ends. So for each of these repeating units that we form, we also produce 2 water molecules. And as I said, you can also do it. So this is using a diol and a dicarboxylic acid, but we could also produce a polyester by reacting a molecule that has an alcohol and carboxylic acid functional group on it, where it just would end up joining end to end. Okay, has anybody got any questions about that? I think it's a good idea to draw it out structurally so that you can see the bonds clearly. I think it gets a little bit lost here. Easier to make a mistake if you're just doing it semi-structurally. But you can see clearly that this is an ester, can't you? Alrighty.